What if I told you that everything you've ever seen, every planet, star, galaxy, all the stuff on Earth, and even the glimmering edge of the cosmic horizon, is less than 5% of what actually exists? It sounds unbelievable. And yet, scientists agree that 95% of the universe is invisible to us, hidden not just from our eyes but from our most advanced telescopes and detectors. This is not science fiction. It's the cutting edge of science today. If that surprises you, you're not alone. About a century ago, astronomers were just starting to realize that the universe was far bigger than we'd ever dreamed. We know that most of it isn't just big. It's mysterious, made of dark matter and dark energy. Two forces or substances so strange that even the world's top scientists admit they barely understand them. How did we discover this cosmic secret? What clues forced us to accept that most of the universe is hidden? And what do these dark components mean for everything from the birth of stars to the fate of reality itself? The story of why we can see 95% of the universe is a detective story on the largest scale imaginable. Let's jump in and start with what the universe is made of and what that actually means. For most of history, people thought that what you see is what you get. The stars, planets, and galaxies seemed to be all there was. Our eyes picked up the visible light. Telescopes later gave us views in radio waves, infrared, X-rays, and even gamma rays. With each new way of seeing, we discovered new kinds of objects: dust, clouds, black holes, pulsars, and more. By the early 20th century, telescopes were peering farther across space and time. Scientists mapped our galaxy, then others, realizing the universe was full of distant, enormous assemblies of matter. Everything we directly detected: dust, gas, planets, people, whales. Ice cream was dubbed ordinary matter or baryonic matter. This is stuff made of familiar particles: protons, neutrons, electrons. Stored. But as our observing tools got better, something wasn't adding up. From the largest groups of galaxies to the smallest motions within them, things consistently broke the rules. Objects were moving as if there was a lot more mass, invisible mass, holding everything together. Only about 5% of all the mass and energy in the universe is normal matter, what you and I are made of. The rest is the deep mystery of the cosmos. The earliest hints that something was wrong in the universe's accounting came almost 100 years ago. In the 1930s, Swiss-American astronomer Fritz Zwicky was studying the Coma Cluster, a tight group of galaxies. He realized that the visible stars didn't exert enough gravity to hold the cluster together. The galaxies were moving much faster than expected. If gravity came from what we could see, the cluster should rip itself apart. Zwicky called the extra mass Dunkelmaterie, dark matter. People figured maybe he'd made a mistake. Jump to the 1970s. Astronomer Vera Rubin and her collaborator Kent Ford were studying how stars orbited in the outer parts of spiral galaxies, like our own Milky Way. Their finding was shocking. Stars far from the center were moving just as fast as those nearer in. According to the laws of gravity, this should be impossible unless there was extra, unseen mass extending far beyond what we could see. Dozens, then hundreds of galaxies have revealed the same pattern. If only visible matter existed, galaxies would spin themselves apart. Clearly, something invisible was providing the extra gravity. A lot of it wasn't just galaxy rotations. Fritz Zwicky and later astronomers looked at entire clusters of galaxies. Studying the speed of galaxies and the hot gas in clusters, they found over and over again that much more gravity was present than expected. This missing mass was about 5 times what could be accounted for by all the stars, gas, and dust. One of the most dramatic confirmations came from a cosmic accident: gravitational lensing. As Einstein predicted, very massive objects bend light. When astronomers see the light from more distant objects bent around a massive cluster, they can estimate the mass of the lensing cluster. The result? The mass needed to explain the bending is way higher than what's visible. A famous case is the Bullet cluster. 2 galaxy clusters collided, sending their gas, which is visible, one way, and the gravitational center measured by lensing, another. The separation tells us dark matter is a real physical thing, not an illusion or mistake. The cosmic microwave background, patterns from the dawn of time. Everywhere we look in the universe, we find a faint radio hiss. The cosmic microwave background, CMB. This is leftover light from when the universe was only about 380,000 years old, released just after atoms first formed and the cosmos became transparent. Modern satellites like COBE, WMAP, and Planck have measured tiny temperature patches in the CMB. These variations, mapped all over the sky, aren't random. They give us a snapshot of the infant universe. To explain the patterns, astronomers build models. They tweak the amount of normal matter, dark matter, dark energy, and test until everything matches. The catch is, without dark matter and dark energy in the mix, the models don't come close. The best fits show the universe is about 5% normal matter, 27% dark matter, and 68% dark energy. The expansion of the universe. Something's pushing outward. For a long time, scientists expected the universe's expansion to slow down. After all, gravity pulls things together, right? In 1998, two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, used supernova-specifically type EA, your reliable cosmic standard candles, to measure distances to distant galaxies. Their result was shocking. The universe's expansion was accelerating. Instead of slowing down, galaxies were racing away faster and faster. This implied that some form of anti-gravity was at work. Physicists called this mysterious force dark energy and estimated its share of the universe at about 2/3. It turned out there was not only invisible matter, but also a weird kind of invisible energy dominating the universe's future. Dark matter. The universe's invisible glue. What is dark matter, and how do we know it's there? To distinguish it from the ordinary stuff that makes up stars and planets, scientists call this hidden mass dark matter. But don't be fooled. Dark just means invisible to our forms of light or electromagnetic radiation. Here's what we know about it. Dark matter is invisible. It doesn't emit, absorb, or reflect light. It has mass. It exerts gravity, pulling on normal matter and light. It was critical to making galaxies and clusters. Without its gravity, the universe wouldn't have had time to form its current structures. It isn't made of the same atoms as us. Measurements show the normal matter cannot explain the observed cosmic web. How do we know dark matter exists if we can't see it? Scientists use several strategies. Galactic rotation curves. Stars orbit too fast for just visible matter to hold them in. Galaxy cluster dynamics. The speeds of galaxies and clusters show more mass must be present. Gravitational lensing. The bending of light by clusters reveals extra mass. Cosmic background patterns. The CMB fluctuations fit models only when dark matter is included. Large-scale structure. The web of galaxies and voids can arise in time with normal matter alone. Put simply, dark matter is the invisible glue that keeps galaxies and clusters together. Something heavy lurks in space, but we only notice it by what it does to everything else. What isn't dark matter? Early on, some scientists proposed that perhaps this missing mass wasn't so exotic. It might just be black holes, faint old stars, planets, or dust. But careful studies showed that there weren't enough of these objects. Their signals, like the elements made in the early universe, didn't match observations. So what could it be? Weakly interacting massive particles, WIMPs, hypothetical particles that barely interact with normal matter, except through gravity, heavy, invisible, and slow-moving. Ixions, ultralight particles, also hypothetical, which might be cold and slow and run through the cosmos. Sterile neutrinos, neutrinos that don't interact via the usual weak force. Primordial black holes, tiny black holes born in the early universe, though evidence for them being abundant is lacking. Other, even stranger possibilities exist. The key is that dark matter must provide gravity, not interact much with light, and be quite stable. How are we trying to detect it? Given its invisible nature, searching for dark matter is a major challenge. Here's how scientists are hunting for dark matter. Direct detection. Ultra-sensitive experiments deep underground, hoping for a rare interaction between a dark matter particle and ordinary atoms. These are the big tanks of chilled noble gases, waiting for an incredibly faint kick. Indirect detection. Looking for signs of dark matter particles colliding and creating gamma rays or cosmic rays detectable from space. Accelerators. Smashing particles together at high energies, like at the Large Hadron Collider. in the hope of producing dark matter particles that escape unnoticed, leaving missing energy in the debris. So far, no definitive dark matter particle has been found, but new experiments are underway every year. So many scientists are hopeful that a breakthrough is possible. Dark energy. The force we never saw coming, the cosmic surprise. The universe isn't just expanding, it's accelerating in the late 1990s. Teams of astronomers followed distant supernova, exploding stars so bright they can outshine whole galaxies. By carefully measuring how their light shifted toward redder colors and how bright they seemed compared to their distance, astronomers made a profound discovery. Instead of slowing down due to gravity, the universe's expansion was speeding up. Gravity as we understand it should slow things down. Instead, something was acting like a kind of anti-gravity, pushing space apart faster and faster. This was even stranger than dark matter. What is dark energy? Physicists called it. Dark energy, a placeholder name for whatever is causing this expansion to accelerate. Key points. Dark energy makes up about 68% of the universe, more than anything else. It is evenly spread through space, not clumped like matter. Its effects are only noticeable on the largest scales, across millions or billions of light years. We don't know what it is. Is it the energy of empty space, the quantum vacuum, a new field or force, or a flaw in our understanding of gravity? In short, dark energy is what keeps the universe expanding faster and faster. It's the dominant factor in the fate of everything. The cosmological constant and Einstein's blunder, the idea of a repulsive force in the universe, isn't new. Albert Einstein, while formulating general relativity in 1917, added a cosmological constant denoted by the Greek letter lambda, or lambda, to his equations. He thought it necessary to keep the universe static, otherwise, gravity would pull everything together. When it was later found that the universe is expanding, Einstein called this his biggest blunder, thinking the cosmological constant wasn't needed. But, as it turns out, observations in the 1990s and 2000s brought this term back, the cosmological constant. In modern language, is closely related to what we call dark energy. This means that the universe's expansion isn't just about the stuff in it, but also about a property of space itself. What could dark energy be? Scientists have proposed several possibilities. The cosmological constant, an energy inherent to space itself. Space expands, more space is made, and so the total dark energy goes up, but its density remains constant. Vacuum energy. In quantum theory, even empty space is full of tiny fluctuations. Quantum foam. Maybe dark energy is the leftover energy of the vacuum, a new field or quintessence. Some suggest a changing field that fills the universe and drives acceleration. Modified gravity. Maybe our equations for gravity are incomplete, or need to be tweaked at cosmic scales. Each idea has problems, and the true nature of dark energy remains one of science's biggest mysteries. The universe's anatomy, the lambda CDM model, the standard model of cosmology. So how do scientists keep track of all this? Enter the lambda CDM model. This is the standard recipe for the universe. Lambda, the cosmological constant dark energy. Cold dark matter CDM, the main type of dark matter, slow-moving, and docent T, interact with light, normal matter, atoms, light, neutrinos, etc. This model isn't just a guess. It's an incredibly successful fit to data. From the CMB to the expansion history of the universe, the structure of galaxies, and more. But it leaves us with a gigantic question. Why do these components exist? And why are their amounts tuned just so? Evolution of the universe. The role of the unseen dark matter and dark energy weren't just latecomers. Their effects shaped how stars, galaxies, and clusters formed. Dark matter's gravity clumped things together, creating the cosmic web. Dark energy eventually took over, stretching space ever faster and determining the future. Without dark matter, the universe would be a featureless soup. Without dark energy, expansion might stop, and the universe would crunch back together. How do we know it's not a fluke? The evidence for dark matter and dark energy is robust, not just because of one experiment, but because so many eons of evidence point to the same conclusion. Rotation curves of galaxies. Velocity dispersions in clusters, gravitational lensing. Fluctuations in the cosmic microwave background type IA supernova measurements of expansion. Large-scale distribution of galaxies and galaxy filaments, structure formation and simulations and observations. Each of these lines of evidence could have a different explanation on its own, but when they all fit the same model, science takes notice. Alternative ideas. What if we're wrong about dark stuff, modified gravity and MOND? Some researchers have suggested we might misunderstand gravity itself. The modified Newtonian dynamics MOND idea proposes that Newton's laws or Einstein's equations need revision at very low accelerations, like those on the edge of galaxies, which would explain flat rotation curves without invisible matter. Modified gravity theories can explain some observations, especially within galaxies. However, they struggle with others, like the bullet cluster, or patterns in the CMB. Most cosmologists still find dark matter, dark energy, the best fit. Other possibilities: black holes, extra dimensions, and more people have wondered, could the universe be filled with primordial black holes? Could extra unseen dimensions or hidden particles do the trick? Some suggest the dark fluid idea, unifying dark energy and dark matter in one stuff. None have yet worked as well as our standard model, but the search continues. The limits of knowledge. Fine-tuning, the multiverse, and existence. Why is the universe's composition so special? Here's another weird thing. If the numbers shaping the universe were even a little different, our existence might be impossible. If dark energy was much bigger, galaxies and life couldn't form. If dark matter or ordinary matter were different, the cosmic web would never have arisen. Our universe would be empty or chaotic, or would have collapsed before stars could light up. Why this fine-tuning? There are a few possibilities. Coincidence? Maybe things just happen to be right for life. Anthropic principle. We observe a life-permitting universe because we couldn't be here otherwise. Multiverse. Perhaps there are countless universes with different properties, and we live in the one that allows us to exist. No one knows. The multiverse remains controversial, maybe untestable, making it more philosophical than a scientific idea. But it helps explain why the cosmic recipe seems tuned just so. The cosmic web. Large-scale structures and dark matter's hidden hand. What the universe looks like on the largest scales as astronomers map the universe. They find that galaxies and clusters aren't evenly spread out. Instead, they form gigantic filament strands and sheets separated by vast voids. This cosmic web is hundreds of millions of light-years across. Computer simulations confirm that, to get this kind of structure, dark matter must be present. Gravity acts as scaffolding, shaping galaxies and clusters. In fact, astronomers have now detected dark matter on the ends of these web-like filaments by observing slight gravitational lensing effects, yet another confirmation that the invisible outweighs the visible. Observing the invisible, new maps, new eyes. Telescopes like the Hubble Space Telescope, Planck, and upcoming missions like the Nancy Grace Roman Space Telescope and the Rubin Observatory use gravitational lensing, supernova mapping, galaxy surveys, and more to probe the unseen. These efforts are making more detailed maps of dark matter, searching for new clues, and attempting to measure how dark energy might change over time. The quantum vacuum, inflation, the birth of the universe. Nothing isn't really nothing. One of the strangest ideas from quantum physics is that empty space isn't really empty. Even in a perfect vacuum, particles constantly appear and vanish, borrowing energy from nothing and then returning it a jittery quantum foam. Some physicists propose that dark energy is really this vacuum energy writ large, but calculations of how much vacuum energy should exist predict a number way too big. 120 orders of magnitude larger than what S observed. Why is the actual vacuum energy so small? This is called the cosmological constant problem. It's one of the worst mismatches between theory and observation in science, inflation and the early universe. According to the inflationary theory, moments after the Big Bang, the universe expanded exponentially faster than the speed of light. Inflation helps explain the uniformity of the CMB and cosmic structure. Inflation could have been driven by a kind of dark energy, but only briefly. Inflation also raises the idea that our universe may be just one in a vast multiverse, where different regions have different properties. The Hartle-Hawking and quantum birth models some Cosmologists have suggested the whole universe could arise spontaneously from a quantum vacuum. The no-boundary proposal, developed by Stephen Hawking and James Hartle, describes a universe without a sharp beginning. Just as space curves smoothly, so can time. It's mind-bending stuff, and deepens the essential mystery of why is there something rather than nothing. Key scientists in the mystery of the universe's dark side, Fritz Zwicky. First to propose dark matter,
1933 by observing galaxy clusters. Rubin and Kent Ford. In the 1970s,
discovered flat velocity curves in spiral galaxies, providing key evidence for dark matter. Saul Perlmutter, Brian Schmidt, Adam Rees discovered the accelerating universe, confirming dark energy's existence. Nobel Prize in Physics, 2011. Nancy Grace Roeming, mother of Hubble, key in developing modern space telescopes. Albert Einstein, introduced and later doubted, the cosmological constant, now key to understanding dark energy. These scientists and many more push the boundaries of what we can know about reality. It's how we tell the story. Science communication and the power of narrative. This story isn't just numbers, particles, and theories. It's also about how humans ask and answer questions, how we face our ignorance, and how we use storytelling to convey the wonder and weirdness of reality.